Okay, we gotta be there now. Welcome back to Cloud 42, I'm James. I am in the middle of developing an electronic lead screw for my lathe, which is a device that replaces the change gears with an electronic controller and a motor. If you haven't seen the other parts of the video series, you might want to check those out first. Today we have reached a pivotal point in the project. We have a prototype for the electronics, we have working software, and we have the motor and encoder mounted on the lathe. Now it's time to make some chips and see if this thing comes together. Okay, I had two different motors that I wanted to try. You'll remember from the previous video, a NEMA 24 stepper and a NEMA 23 servo motor. What I have mounted on the lathe right now is the NEMA 24 stepper motor, and I've got two 48 tooth pulleys, one 3D printed because I ordered the wrong bore size and the replacements are not here yet, and the other is a proper aluminum 3M pulley, high torque drive pulley directly on the motor shaft. So this is geared 1-to-1. Then there's also a gearbox in the lathe, and it's set up also for 1-to-1. It's possible one of these is, I think, a 4-to-3, or maybe it's a 5-to-6 ratio, either increasing or decreasing, and the other one is a 2-to-1 or a 1-to-2. So you can switch this to a mode that'll double. I think C doubles, and on B it cuts the speed in half. So we have some other options we can use for gearing, but for now I've just got it set 1-to-1 all the way through. I've also made some marks on the pulleys, so maybe you can see this in the video. There's a mark here on the shaft going into the lead screw, and I've got a mark up here on the pulley that's coming off of the spindle so that you can see how those are turning. Now, unfortunately, this pulley is not turning 1-to-1 with the spindle, it's actually turning slower, and then there's a multiplication with the belt. So the encoder is running the same speed as the spindle, but this pulley is not necessarily. But you can at least see that they're turning. So let's set up some basic cuts and see what we can do. I've got this set to 5 thousandths per revolution, and I've got a piece of material in here. This is 3/4 inch 1018 mild steel. And let's just take some cuts on it and turn this down maybe to 1/2 inch so we can try to cut a 1/2 inch thread on it. Let me find my zero here, going nice and slow. Okay, and let's just start by taking 10 thousandths. We don't want to overwhelm the stepper with the feed, and I don't really know what it's going to do. Let me bring the speed up here. That's about 1200 RPM. Let's just take a cut. That seems to be handling that just fine. Let me bump this up to 7 thou per revolution, and let's take maybe 15 thou depth of cut. Okay, that was easy. Let's take another 15 and let's go faster. Okay, so far so good. It's just behaving like a lathe, which is exactly what I want. And I'm going to target 1/2 inch for this. And we've still got a ways to go. I'm still well over 650. Let's try taking something a little deeper. Let's take 20 thou depth of cut. And again, I'm going 7 thou per revolution. Let's take 25 and let's bump it up to 8 thou. And of course my compressor just kicked on. Okay, we need to take off about another 75. So let's take, that'd be 40. Let's take off 50. And yeah, I'm really pleased with this. That's a pretty good feed rate. And let me go ahead and bump this back down since we'll go ahead and take one more roughing cut. Then we'll dial this back down to 3,000ths per revolution for a finish cut, and we'll take half of what's left. It looks like we've got 24, so we can take 12. Actually, that'll take us right to size because this is doubled. Okay, so we need to take 24, so take 12, so I'll take 6 on the dial. And this should be half of what's left. Now I'll go ahead and run this even a little bit faster. 3 thou per rev finish cut. And that should put us right at ½ inch. And what do you know? It's right at ½ inch. Okay, let's do some threading. Half 13, anyone? Bring in a carbide threading tool here. And let's start by making a gutter to run off into, and we do not have to run it that fast for that. That should be plenty. Now let me just get my 0 here. Now if you haven't noticed, I'm not, being super careful with this. Let's switch over to thread mode and go to 13 threads per inch because I have a half 13 nut here that we can use to test. Okay, so let me set 0 on my cross dial, and I've already got 0 on the compound. Let's take 2 thou just as a scratch pass. So far, this servo is performing well. Let's check that and make sure that looks right. That looks right to me. Okay, let's take, not on that dial, let's take another 5 and see what that looks like. Speed it up a little bit. And actually, I wasn't paying attention to which number I started on, so we probably are going to have a scratch. Funny. Pay attention to the threading dial now. Okay, that's starting on number 1. Sure enough, that's slightly out of time because I didn't pay any attention. We'll pay attention now. Let's take 8 thou now. That's nice. Let's take 10 since we're still at the beginning of the thread and it's easy. You can hear the lathe bogging down just under the load of the cut, but you can see, hopefully, that the timing is still perfect because the microcontroller is reading the spindle 4,000 counts per revolution and keeping up. Adjusting in real time. Let's go a little faster. Let's actually take a cut this time. Take 5 here. Another 5. Another 5. And another 5, and I'll wait for my number to come around here. And there we are. Oh, there's almost no rock. I hit it exactly right. Accidentally. Wow, that looks really good. I'm really pleased with that. Gonna try something finer. I'll try 1/4 28. Hey, let's try 1/4 28. Switch back to feed. Okay, here's a piece of mystery metal, some kind of steel. Let me just stick it out the same amount so that my focus will be close. Now let's start by turning this down. Okay, that puts us 3 under, it'll be fine. Okay, and let's switch over and thread 28 threads per inch. So switch to threading and go to 28. Okay, we'll call that 0. Okay, we'll take a 2/1000 scratch pass. Yep, looks good. Okay, let's take a little bit here and see how it looks. Five more. Okay, I'm not sure what this material is, but it does not like to cut. Okay, well, I think that is to size. 1/4 28 nut. And there you go. Beautiful. Okay, well, I am very, very pleased. I'm not pleased with this material. It was hard to cut. I think it's stainless. It's some mystery metal that came out of a junk bin at work, I think. So that worked really well. Motor's just a little warm, you know, similar to what I would expect if I were running it on the mill. I'm actually really surprised. I was expecting, after all the comments and after all the discussion, to have a lot of trouble with this motor running 1-to-1, but so far that looks good. Can I stop it? Is there a limit? Yeah, absolutely. But this is really, for all practical purposes, the kind of thing I do. We just cut half 13 threads in steel. We tried a bunch of different feeds. We were feeding fast with relatively heavy cuts for this little lathe, and then came back and cut some very beautiful looking half 13 threads, and then turned down another piece of material and cut 1/4 28, and I didn't change a single change gear. I just hit the buttons on the controller. So I'm really pleased. This is working really well. Let me swap out for the servo and let's try that again. Okay, I got the motor swapped out. We now have the servo in here instead of the stepper, and you can see because I've got the servo, I've now switched to a 3-to-1 belt drive. So this is a 24-tooth pulley here and a 72-tooth pulley on the lead screw. Let me grab my pen and put a mark on that just so you can watch what's happening. There, can you see that? Yeah, you can see that moving. Okay. I am set right now to 5 thou per revolution feed rate. Now, ironically, the servo seems to make more noise, at least this servo seems to make more noise than that stepper with that good DSP driver. So I'm not sure exactly why that is, but the stepper did fine. Let's see how the servo does. Same drill, we'll take this piece of 3/4 inch down to a 1/2 inch. Start with a nice light cut, maybe 10 thou. Do this about 1,000 RPM. Handling that just fine. Let's go right to 20 thou. And again, now we're up to about 1,200 RPM. That was 20 thou per side. Let's just take 25 and just see what happens. Oh yeah. Okay, let's see where we are. Oh, that makes a beautiful finish. So far, servo's working great. 635, which means we need to take another 67. Let's go ahead and take 30 and just see how that does. Oh, no problem. Okay, so the feeds are working great. Let's switch to threads, and let's go to 13 threads per inch. And let's cut a half 13 thread on this thing. Okay, a nice wide gutter just so there will be no drama. There we are, just touching, 2 thou. Looks right. Looks like I did the math right. Okay, let's take the rest of the first 10. Let's take 10 more. Go a little slower than that just so I can hit my numbers. Right in time. Let's take 10 more. Now what you heard there is interesting. I'm running this on a 1200 RPM belt, but I'm dialing it way down with the VFD to what? About 220 RPM. And so it's running very slow. So when I entered the cut with a nice heavy cut, it slowed down quite a bit. But because I'm reading the spindle 4,000 counts per revolution, it just tracked perfectly with it. You can see there's no issue at all with the timing, even though it radically changed speeds during the cut. Okay, this goes a little faster, and we start taking 5 at a time now. Okay, we got to be there now. And well, that is just about right. Just a tiny bit of rock in there, and that's just because I missed all the way down to the bottom. So there's another perfect half 13. Well, I am really happy with this servo and the way it's performed. It's quite a bit smaller than the stepper because it's a NEMA 23 as opposed to a NEMA 24, which is some kind of odd size that comes mostly from Chinese manufacturers. But this is running quite a bit cooler, even though it's smaller and has less surface area to dissipate the heat. And that would make sense because the servo driver is going to run less torque through it when it doesn't need the additional current to keep it in sync. As long as it's running fine and staying in sync, it's going to run with a lower current and only peak the current when it has to keep it in sync. So I'm pretty happy with that. There's lots of tuning left to do. There's lots of tuning that can be done on the servo. We need to test the limits, see how close we really are on power. But I'm making the kind of cuts in steel that I would normally make with this lathe, and so I'm pretty happy with it in general. Now there are a couple things I've noticed. One is that the servo does seem to be quite a bit louder than the stepper. Let me see if I can get the microphone down here so you can hear it. The stepper was almost silent, but the servo, you can really hear the steps as the thing's going. And maybe that's because this is a hybrid servo and not a real servo, and I'm sure people will tell me in the comments. If you know of an inexpensive real AC servo that you think I should test, throw that down in the comments. Let me know where those are, and I'd be happy to take a look at it. I would love to have like a real AC servo, especially if the price is reasonable, because that's going to be a lot quieter and it's going to have a lot more headroom on the power and a lot more headroom on the speed, as far as I understand it. So that would be something I'd be interested in checking out. Well, there is one other thing that I wanted to test while I'm here, and that is the tachometer. You can see the left 4 digits on the display here read out the speed of the spindle. So as I rotate the spindle, those numbers are changing, and that's the speed in revolutions per minute. So if I turn it on nice and slow, you can see it's reading, what is that, about 135 RPM, 134. It's kind of floating between 135, 134, 136. I may want to do a little bit of smoothing in software. I think that's updating right now 10 times per second. And so that's the real speed that it's reading off of the spindle. Now to verify that's correct, I think it's correct because I know the speed of the microcontroller and I know how fast I'm counting and I'm doing the math, and the timing in the microcontroller is pretty precise for exactly this purpose. So I think it's right, but we need to make sure. So I've got a piece of reflective tape right here you can see on the chuck, and I have a laser tachometer. So this projects a red dot, and every time it passes over that white reflector, it reflects that laser light back into here and it measures the RPM. So let's start nice and slow. We see like 135 down there. Let's test and see what we read here. And you can see I'm reading 135.5, 135.6, 135.6, And if you look down on the microcontroller down there, I'm seeing exactly the same thing. 134, 135, 136, and it's about 135 and a half here. Okay, well, let's speed it up a little. There's 456, and I'm seeing about the same thing on the microcontroller. See if we can hit 1,000 exactly. So there's pretty close to 1,000. We're 1,000 a couple counts over. And on the tach here, I got 1,002. And we're reading, what, 1,002, 1,003, 1,001. I can see flitting around. Let's take it all the way up. Okay, that's the max speed of my lathe. And I'm reading here 2557. And on the controller, I see 2550 something, 2553, 2552. Oh, there we go, 2552, 2553. Wow, those are close. Okay, I'm impressed. That's really close. And just for sanity's sake, let's spin it all the way up and let's go in reverse and just make sure I didn't do anything dumb on the math there. Well, I could not be happier with that. Between the inexpensive import tachometer and using the internal oscillator in the microcontroller, I honestly expected to have a little bit more error than that. I am very, very pleased to see how close that tachometer is. I couldn't be happier with that. And so the other thing that tells us is that even when we're running the spindle at 2,500 RPM or 2,550 RPM, we're not losing counts. And let's talk about what that means. So if we're running 2,550 RPM, let's divide that by 60, it means we're turning the spindle 42.5 times per second. But since this encoder is counting 4,096 counts per revolution times 4096, that means we're registering 174,000 counts per second over this cable in this noisy environment to that microcontroller, and it is counting them accurately. And we know it's counting them accurately because our threads stay synchronized over multiple passes when cutting threads, and because the tachometer is coming out just dead on accurate. So I'm pleased. The electronics have been proven. The software has been proven. These motors have been proven to a point. We need to find out ultimately where the limits are, when the servo will lose synchronization and fail due to lack of torque, when the stepper will lose steps, and try to decide, are these motors big enough for this application, or do we want to go to something a little bit more powerful? But ultimately that doesn't matter because the driver and the motor can be swapped out freely. The electronics and the software and the encoder can stay the same. So what do we still need to do? We need to figure out the motors. We need to figure out how to mount the motor back in here where it's more convenient. We need to figure out a PC board that'll make this easier to put together so we don't have all this stuff all over the place. And we need to finalize the enclosure. I've got a viewer sent in, we'll see this in a future video, sent me some red filter material that'll stick onto this display to make it easier to read. And all of this is coming in future videos. Stay tuned. If you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.